let's go ahead and take a look how light is going to react as it goes from one medium to another. So what we're going to need is, first of all, our speed of light equation, which is going to deal with the index of refraction, which is going to be n, and c is our speed of light. Speed of light in a vacuum, so like space, and v is the velocity of that light in the new medium. We'll also need Snell's law, which is going to give us the angle of refraction if we know our indices. So n is the index of refraction in each medium, and our angle is the incident angle and also the angle of refraction. Okay, so we have a pool that is 100 meters long with two lights mounted on one end. One light is underwater, the other light is above the pool deck, and how long does it take the light to travel from one end of the pool to the other? So presumably our situation is that we have, like, this is our pool, and we have like a light bulb right here, and then beneath the water we have another light bulb, and the light is going to travel to the other end of the pool, and we want to know how long. Is there a difference? Well, there's definitely a difference. It's very small in how long it takes the light to get to one end to the other. So we are going to first use not Snell's law, but our velocity formula right here. So we're going to plug in c. Now c is 3.0 times 10 to the 8th, and we'll divide that by our index of refraction. So in this case, 1.000293, and that will give us our velocity. Now, again, this is the velocity of light in a vacuum, and as we get our velocity, our new velocity, it should slow down because the fastest light can go is in a vacuum. So I am just typing this in to the calculator to solve the speed, and I get 299,912,125.7 meters per second. And now what we want to do is we want to find the time it takes to get to the other side. So I can use a position formula. So this is our position formula. And we actually don't need all of it. So we don't need our acceleration piece because it's not accelerating. We don't really need our initial position because it's just always going to be 0 for these. So our final position is 100 meters. Our velocity is 299,912,125.7. And I'm going to divide both sides by the 299,912,125.7. That right there. So when I type that in, that will give me a time. Now it's going to be a very, very small time. And I get a time of 3.3343 times 10 to the negative 7th. Now my calculator spit out an E minus 7. That's what it means, scientific notation. So that's our time. And now let's do it for the water. So that's the time for the above water. Let's do the time for the in-water light. So first I'm going to have to find the velocity of the light. And use our new index of refraction. So we get a new velocity of 22,556,390,9.8 meters per second. And now we're going to use our position formula, so 100. So I'm using XF equals VIT. So I'll plug each of these in and divide by this large number here. Now we do expect it to go ever so slightly slower, and that number right there. So if I do 100 divide I get 4.43 repeated times 10 to the negative 7. So what does that mean? 4, 4, 3, and I take this decimal point that's right here. I'm going to move that left 7 times. That's what that minus means. 1, 2, 3, 4, 5, 6, 7. There we go. So a very small amount of time. But it is a little bit more than this one over here, than the light. So the light in the air gets there ever so slightly sooner. All right, so the speed of light through a certain material is found to be 2.0 times 10 to the 8th. What is the index of refraction? And how long would it take it to travel through a 500 kilometer material? So first, let's change that to meters. We'll do that by multiplying by 1,000. So that's how many meters we have. So first thing we're going to do is we're going to find our index of refraction, because that's the first question that is asked. So we have 2.0 times 10 to the 8th on the left-hand side. We have 3.0 times 10 to the 8th as our speed of light in a vacuum. And I will cross multiply. So I have 2.0 times 10 to the 8th, n equals 3.0 times 10 to the 8th. And I'll divide. And that will give me n. So after I type that in, I get n equals 1.5 is my index of refraction. All right, well, now let's find our time. So we don't need our whole position formula. We just need this portion. And so we have 500,000 as our final position. Our velocity is 2.0 times 10 to the 8th, and time. So I'll divide both sides by 2.0 times 10 to the 8th. So type that into the calculator. And get 2.5 times 10 to the negative third is our time. So what is that? That's 0.0025 seconds when I move my decimal point 3 times. Okay, so a beam of light is traveling through the air and hits the boundary of a new medium at a 55-degree angle. Find the angle of refraction if it passes through each one of these materials. Now notice each of these have an index of over 1, which is what we would expect if we're going through anything besides a vacuum. But here's what's just a really important thing to remember is that we expect as light passes into an index that's higher, it should slow down. And if it slows down, it should bend toward the normal. Okay, now what that'll look like is if, say, we have our water. I'll draw up here, but say this is the surface of our water. Our light comes in. Here's our normal. And this is our angle of incident. And since we're going from basically air to water, the light is going to slow down, so it's going to bend towards this line right here. So this is our incident angle, and this is our angle of refraction. Okay, so we're going to use Snell's law. And we're just going to plug in all the information that we have. So this is our N1 right here. So 1.33. Our angle is given to us in the problem. 55-degree angles is our angle of incident. Our index of refraction. Actually, now this was not N1. What am I talking about? This is my N2. My first is right here because I'm going through air. So 1.00293. This is my N2. So my N2 is 1.33. And now sine of my angle. Okay, so I'm going to divide both sides by 1.33. And when I go to type it in the calculator, I'm going to do this portion first right here. So 1.000293 times sine of 55, make sure you're in degree mode, and then we'll divide that by 1.33, and that gives us 0.6161 equaling the sine of our angle of refraction. So we're going to inverse sine both sides, and that will give us our angle of refraction. And I get 38 degrees. We have bent towards the normal, just as expected. I'm going to go ahead and clear off this mess, and let's do the next one. So we have a high index here, a diamond. So this is our N2, and we're going to put in 1.000293 sine of 55. That's coming from right here. Is going to equal 2.42 times the sine of our angle of refraction. We'll divide both sides by 2.42. And in a moment, we'll be doing inverse sine. But first, again, we're going to type this portion into our calculator first before we do any dividing. And after it's all said and done, we get 0.335 or 859. And then when we inverse sine that, we get 19.79. So notice, well, I erased it, but it's a lower angle, and that's because it's bent more towards. So if I exaggerate my diagram, say that's my normal, and say this is my surface. So my normal comes under the water here, or whatever, the diamond. Here's my thing. My light comes in and is bent towards, is going towards that normal. Okay, last one. So same setup, basically 1.000293 sine 55. So it's not always a 55 though, it depends on our incident angle. It's going to equal 1.66 sine of our incident or our angle of refraction. We divide both sides by 1.66. And we type all of that in, making sure to do the numerator first. Then we'll divide by our index of refraction. That's a 3. And we'll inverse sine to get our angle. And our angle of refraction is 29.57. A beam of light is traveling through water. There's our index of refraction. It encounters the boundary of a new medium. It hits at a 40-degree angle and has been found to have bent 30 degrees. So maybe, let's say it's oriented like this. And let's say this is our water, and this is our, whatever material. So our water comes in, or our light comes in. Here's our normal. And our incident angle is 40 degrees. And then it's bent towards. So this is 30 degrees. So since it bent towards the normal, we expect an index that is bigger because the light has slowed down. So we're going to use Snell's law and just plug in what we know. So we know our index in water is 1.33. We have our sine 40. We're looking for this N2, our new index, and we have sine of 30. So I'm going to divide both sides by sine of 30. And again, I'm going to make sure I type this numerator, all of it first. And then I'm going to divide by the sine of 30. And I get 1.71 after rounding. the angle of refraction of a light ray traveling from air is there, and into flint glass is 35. What is the angle of incidence? So let's say this is my boundary between my mediums. Here's my normal, and what has happened is our light has come in at some angle. We don't know what that angle is. It is bent towards the normal. So here's our 35 degrees. So we want to know, well, what was the incident angle? So we're going to have 1.000293 sine of our angle equals 1.66 sine of 35. So I'm going to divide both sides by the 1.000293. And I'm going to have sine of my angle is going to equal this stuff. So I'm going to type all of that in. And I get sine of my angle is 0.951857. I'll inverse sine that. And when I inverse sine it, I get about 72 degrees. Okay, and I'm not paying much attention to my significant figures right here. All right, so that wraps up this section.